Hello! Advances in healthcare are often the result of advances in medical science combined with advances in technology. Proton therapy in the treatment of cancer is an example of such a technological advance. In Delft, the building of the first treatment center for proton therapy in the Netherlands has started. Two Dutch medical centers, Erasmus Medical Center and Leiden University Medical Center, work together with the Delft University of Technology to realize the Holland Particle Therapy Center. Every year, about 100,000 people in the Netherlands are diagnosed with cancer. More than half of all cancer patients require treatment with radiation in order to halt the growth of their tumors, radiotherapy. Established radiotherapy techniques direct a beam of high-energy X-rays at the cancer site. In recent years, however, more and more patients around the world are treated using a beam of charged particles such as protons to eradicate the tumor.
A major challenge in treating cancer by radiotherapy is to focus as much as radiation as possible at a target, which is a tumor, but at the same time keep the radiation dose deposited in the surrounding healthy tissue as low as possible. In proton therapy, this can be done much more accurately than using X-rays. With the use of more and more advanced techniques in medicine, also mathematics becomes increasingly important. Think of questions like how to construct a 3D picture of a body to locate tumors and organs at risk. What energy and angle should the proton beams have to accurately target the tumor while leaving the surrounding tissue intact? Answering these questions involves a lot of mathematics.
For example, before the start of a radiotherapy treatment, we need to know how large the tumor is and where exactly it is located in the body. For this, doctors use an X-ray technique called X-ray computed tomography or CT scan.
Let's look at how the technique of a CT scan involves mathematics. Suppose we want to detect a tumor in a region of tissue. For simplicity, we divide the region into small boxes. For some tumors, such as lung tumors, the density of the tumor is typically higher than in the surrounding tissue. If an X-ray passes through the tissue, it will be absorbed. The higher the density, the higher the absorption. By measuring the intensity of the outcoming beam, the total absorption in the boxes it passed through can be calculated. From that, we learn something about the density of the tissue the X-ray passed through on the way from the source to the detector. For each ray, this is the sum of the absorptions in the separate boxes. But we want to know the absorption in each separate box. To determine this, we shoot X-rays from several angles through the tissue and measure the total absorption in these angles as well. This gives a lot of relations between the quantities that we can measure, the total absorptions, and the quantities that we want to know, the absorption per box. The relations between the absorption in the boxes and the measured total absorptions are mathematical equations that can be solved. In this way, the absorption of each box can be calculated and hence a tumor can be discovered.
This example illustrates the important role of mathematical modeling. Theory provides relations between quantities that you want to know, in this case absorption per box, and quantities that you can measure, in this case the total absorption of each X-ray leaving the body. But often these relations are not explicit. You will have to solve equations to express the quantities you need in terms of the quantities that you know. Only after that you can calculate and interpret the results.
Another example. When a proton with a certain energy enters a tissue or material, it will slow down and stop, reaching a maximal depth. Physics can tell you how deep it will penetrate as a function of the initial energy. But for proton therapy, you need to know the converse. The proton has to reach a tumor, so you know the desired depth, but you want to know the energy that the proton needs to reach a tumor. So you have to solve the equation.
Equation solving is essential to extract the quantities you want to know from a model. In the following 2 weeks we will show you techniques to attack all kinds of equations and common mistakes that you should avoid. Have fun!